So today we're going to be talking about applications of the Baire category theorem. So remember what's going on. We have this definition of a nowhere dense set. So E is all nowhere dense. If the closure's interior is empty, right? So you take the closure of the set, and you take the interior, look at the interior of that, and if that's empty, then you call it nowhere dense. If a set E is a union of nowhere dense sets, countable unions, countable union of nowhere dense sets, we call it first category, or meager. And if it's not a first category, you call it a second category. So if it's not, it's called second category. Of the first category, of the second category. Okay. And we also have this term generic. If the complement is meager, we call E generic. And the Baire category theorem was that any complete metric space had to be not meager, right? It was a second category. So it's not meager. It's not to say that it's generic, right? It's not saying that it's complement. Its complement is meager, but it's a second category. Those are two different things. So this is the theorem, the Baire category theorem, and we're going to use this today to get some sort of nice results, things that you might have wondered about things that you might have wondered about, and also an important result in functional analysis, the so-called uniform boundedness principle. This is a tool that one uses often in functional analysis. Okay. So we'll do three applications. The first is talking about the points of continuity of a limit of continuous functions, right? So you have a bunch of continuous functions, and you are looking at, they converge pointwise to some function. Okay. And you're wondering, that function need not be continuous, right? But you're wondering about the points of discontinuity of that function. And it turns out that the points of discontinuity of that function are meager. Okay, the set of points of discontinuity of that function are meager. Okay. So it's continuous, on a large set in some sense. The second application we'll be seeing is that that continuous nowhere differentiable functions. So you have some continuous functions, right? Some of them are differentiable and some of them are not differentiable. Right? In the 19th century, Weierstrass came up with this nowhere differentiable function. Right? One famous example of a fractal-like nowhere differentiable function. Right? And so the question is, is that common or is that not common? And in fact, what we'll see using Baire category is that such functions form a generic set among the set of continuous functions. So in fact, continuous functions that are differentiable are meager. So there's nothing in them. So it should be actually not too difficult to create continuous functions that are nowhere differentiable. They're more common. They are common. The last one is this thing called the uniform boundedness principle, which is you have a Banach space, and then you have a bunch of continuous linear functionals on the Banach space. Okay. In the Banach space, you have linear functionals. You have some set of linear functionals on the Banach space. Okay, and these linear functionals are pointwise bounded. So at every point, if you look at the supremum of the values of the linear functionals at that point, so take a point in the Banach space, look at the linear functional acting on that point. Okay. Suppose that for each point in the Banach space, that set of values is bounded. Okay. That set of values is bounded. Then it turns out that the operator norm, the supremum of the operator norms of those linear functionals is uniformly bounded. Okay. This is actually kind of maybe sort of shocking, right? So if at every point the numerical values are bound, the supremum of the numerical values of the linear functionals acting on that point is bounded, then in fact there is a uniform bound on the operator norm on the set of linear functionals. Okay, so this is the uniform boundedness principle. It sounds really magnificent. It's actually pretty simple. It's actually pretty straightforward with using Baire category. So those are the three applications. So I'm going to talk about today. So let's do it. So okay. So here we go. Points of continuity. Of a limit of continuous functions. So you have some complete metric space. And you have a sequence of continuous functions. You have a bunch of continuous functions, and you know that that at each x and x, the limit exists. Fn converges to some function f of x. Okay. So in that case, so we're interested in the points of continuity of this guy. We know that that's not necessarily a continuous function. Right? We know that if the convergence is uniform, right? You know from real analysis, if the convergence is uniform, then this guy's going to be continuous, right? But here we just have pointwise convergence. What can you say about this, about the set of points of continuity of this function? Well, in fact, the set of points, then the set of points of discontinuity of f is meager. That is, it's a union of nowhere dense sets. Okay, so let me phrase it like this. Okay, so let's introduce the notion of oscillation. Okay, so let omega f r x denote the supremum over the ball of radius r centered in x of f of y minus f of z for any, oops, this should be z. Oops. Can't stop writing x for some reason. The supremum over all pairs of supremum of all of values for pairs of points in the ball. Right? So like, basically the diameter of the image, the diameter of the image of the ball. So it's saying how much this function can differ over that ball. And then we define the oscillation of f at x to be the limit, the oscillation at a point. The oscillation at a point is going to be the limit as r goes to 0 of these omegas. So you let the ball, you take the limit, let the radius of the ball decrease to 0, and you're measuring the oscillation of the point, the oscillation of the function at that point. So you see that's going to tend to some value, and it's a decreasing function. It will tend to some value, and that will tell you how much the function is jumping in a ball in balls centered at x. So that's the notion of oscillation. Okay. Here, what's up? Anything else? No? Okay. Okay. So first we notice one that oscillation of f at x equals 0 is the same thing as saying that f is continuous at x. Right? It's obvious. Right? Oscillation is 0. It's basically the same thing. It is the same thing as saying the function is continuous at x. And the second thing you notice is that if we let E sub epsilon be the set of points where the oscillation is strictly smaller than epsilon, then this set is open. Right, I think that's pretty obvious, right? Because right, if you have some point x in the epsilon, then you know that for some ball centered at x, the supremum of f of y and x of z is smaller than epsilon for all yz in that ball. It's called BRS. You know that there's going to be some ball where the jumping is such that the oscillation of the ball is controlled, and then certainly if x star is in the half ball, we have x star is in E sub epsilon. Because here is x, it lies in the epsilon, right? So you know that the oscillation over the ball is controlled by epsilon, right? Well, if you take anybody in the half ball, right? Well, then you can, for that guy, the balls of radius less than r/2 are contained in the ball where the oscillation is controlled by epsilon, right? So the oscillation at that point is going to be less than epsilon, right? So it's straight. I'm sort of shocked that Stein would even say this, given how free he is in the previous chapter. It's almost would say, and it's obvious that such a thing. Okay. Okay. So what are we going to do with this oscillation? we're going to use this definition to create a bunch of sets whose union exhausts the space. Right? We're going to create a bunch of sets whose union is all of X. Right? Right. So. Right. So what we'll do is. So let f sub n be E sub 1/n complement. That is, it's going to be the set of points where the oscillation of f is bigger than 1/n. Bigger than equal to 1/n. Okay. We know that as then the union of all these guys, then the union of the f sub n's is going to be all of so then, I'm sorry, we're not exhausting X. Sorry. What I said was crazy. Okay. We're interested in the set of points of discontinuity of F. Let's call it point D. Let's call it point D. The set of points of discontinuity. Okay. So notice that if you're a point of discontinuity, that means that the oscillation is positive there. Right? The oscillation is positive there. And so, any point of discontinuity is going to lie in one of these sets. Right? So we're going to say, let's consider D as the union of the F sets. If you're a point of discontinuity, well, you're going to lie in at some point, as n gets big enough, you're going to be trapped in that F sub n. Okay? And so this gives us a way of expressing D as a union of sets. Okay. So right. Each of these guys is closed. Right. Note that each guy is closed. Right. It's complement of an open set. So each is closed. And each of these guys is closed. And so what we're hoping to do is see that each of these guys is nowhere dense. Right. So that is that the interior is empty. Right. So it suffices to show that the interior of each guy is empty, because then we'll have expressed the set of points of discontinuity as a union of nowhere dense sets. To do that, we'll require the following lemma. So that is let X be a complete metric space, and again, Fn be continuous functions on X such that Fn goes to X, goes to f of X at each point. and let E be any open ball. E be any open ball. Yes. Okay. Then the claim is that then, given any epsilon, there exists an m greater than equal to 1, and so m is some natural number, such that f sub n of x minus f of x is controlled by epsilon for all x in the, so I should say, then there exists a smaller ball contained in B such that, given any epsilon, there exists an m such that this happens. Okay, so the picture is that you have some open ball B, right? And you sorry, phrased it, I've written it backwards. That's too strong. Given any epsilon, there exists a ball B such that that would just be too crazy. That would be wrong. And wrong. You see that would be way too strong. Okay, so this ball given, so you have any ball. Given any epsilon, there is some tiny ball inside here in which, and an m such that the limit function differs from this f sub m by so, right, that is, the difference in the suit norms between these guys on that little ball is small. Okay, so your function is, given any epsilon, you're guaranteed some tiny ball. You don't know, it may be really tiny, but you're guaranteed some tiny ball on which your function is basically one of the other guys. One of the things in the sequence, one of the numbers in the sequence. Okay. So try to keep in mind where we stopped in the argument. Right now we're going to prove the lemma, and we'll come back to the argument. No, actually, let me complete the argument, and then we'll prove the lemma afterwards. I think that'll be easy to follow. Okay. So suppose we've proved this lemma already. Okay. We will in a moment. Okay. So okay. Okay. So right, we want to show. So hold on. So we want to show that each of these guys has an empty interior. Right? We want to show that each of these guys, each of the f sub n is nowhere dense. Okay? So well, suppose that for some suppose that one of them is not nowhere dense. That's not to say that it's dense, but that it's not nowhere dense. Those are different things also. Okay. Well, in that case, so it's not nowhere dense, right? I.e., has a non-empty interior. That is to say that there exists a ball, open ball B, contained in that particular Fn. Okay. So we're going to see that this leads to a contradiction using this lemma. Okay, what do you say? Well, using the lemma, use the lemma. Take epsilon to be 1 over 4n. Okay, so that guarantees us, here's our ball contained inside of Fn, and so we have this tiny ball, V naught, on which your function is basically one of the FMs. Okay. So then there's this V naught and B and some M natural number such that fmx minus fx is smaller than 1 over 4n for all x in the world. B is continuous. I'm sorry, Fm itself is continuous. Right? We've approximated our non-continuous function. We've well approximated our non-continuous function by one of the continuous members of the sequence. It's continuous. So there's this an even smaller ball, B prime, inside of that B naught, such that fmy minus fmz is controlled by 1 over 4n for all yz and B prime. Okay, but then you see what happens, right? Right, the oscillation of Fm is controlled on that little ball. Right? The oscillation of Fm is controlled on that little ball, and also on that little ball, the soup norm difference between Fm and F is small, right? Which means that the oscillation of F is controlled on that ball. Right? But on that ball is the place where the oscillation is bigger than 1 over n, right? So you get a contradiction. Okay, let me write it out. Plus for all yz in that little ball, right? F of y minus f of z. Right? We're going to show that the oscillation is, we have control of the oscillation of f there. Right? Of course we have control of the oscillation of Fm, it's continuous. But we have this little ball on which Fm and f are close. Okay? So this is controlled by f of y minus, in the standard way, fmy plus fmy minus fmz plus fmz minus f of z. Right? This thing is controlled by 4n, by the continuity, by what we just said. Right? And these guys are each controlled by 1 over 4n, because we're in B naught. And so that gives you that this thing is all smaller than 1 over n. Smaller than 1 over n, and that's a contradiction. That would mean the oscillation for points in inside the 1/2 size ball of B prime is smaller than 1 over n. straightforward. I hope you're all enjoying yourselves. Oh, I just like saying, so easy. Should I just let you guys take over the lectures for the rest of the term? I'm considering it. If you could practice. Chen, do you want to give a lecture? Would you like to give a lecture? It's up to you. It's up to you. If you want some practice giving a lecture, I'd be happy to let you give a lecture. Let me know. Think about it and let me know. Because it's good practice. You know, CGU students don't have a chance to do any teaching. Previously, when I had a CGU student as a TA, I let him give some of the lectures. And then I criticized him. For his own good, of course. Okay. Okay. So we need to prove this down. That f, you can find some little ball on which f is well approximated by one of these epsilon. Okay. And so proof of the lemma. Again, we'll use the Baire category theorem. Let y contain to be a closed ball. And thus a closed metric space. I'm sorry, a complete metric space. Fix epsilon. We're given that epsilon. Let Isabelle be the set of points in Y where the supremum over all, the supremum of S of j minus S of k of S is smaller than epsilon for all j, k bigger than or equal to L. So Isabelle is the set of points where over all pairs of indices bigger than L, the difference of the function at that point is smaller than epsilon. The difference of these two functions at corresponding functions at that point is smaller than epsilon. Right. So we have fnx going to fnx, right, for all x in Y. So you know, if you take your L, if you have some point x, if you fix some point x, at some point for L big enough, your x is going to lie in that Isabelle. For each x, x will lie in Isabelle for some sufficiently large L. That is to say that, again, we have a way of expressing these sets exhaust Y. Now we use the Baire category theorem, right? Y is a complete metric space. We have, and notice that yeah, notice that each of these things is closed. So the example again. One of the, at least one of the epsilon is not nowhere dense. Is it obvious that this is closed? It's obvious, right? Because you're just taking an intersection of sets, of closed sets. Right? You look at each pair JK, the sets where, for each pair JK, you smaller than epsilon. That's a closed set. You're taking the intersection of all over all JK plus the greater than L. Right? So that's going to be closed. It's an intersection of closed sets. So, well, one of these guys is not nowhere dense, right? So there exists on a piece of M that contains an open ball D naught. That ball is going to be the ball we want, right? For all x in D naught, we have that, of course, the supremum of fj minus fk x jk bigger than or equal to n is smaller than or equal to epsilon. For all jk bigger than or equal to n. Right? So take j to n and let k go to infinity. We know that s of m minus s of k minus m then is less than equal to epsilon for all x in that ball. So that's the end. Any questions? No, right? No questions. That's actually very bad teaching to say no. It couldn't possibly be any questions, because then that sort of shuts down any possibility of questions. Are there any questions? No. Shoot. Sorry. Yes. I'm glad you feel very comfortable. Yes.
You don't need the image to be the complex numbers, do you? Like, it's fine for a
that's what we for real numbers.
Metric space.
Oh, well, let's look for an arbitrary metric space. I think so. Yeah, I think so. Slower up. I'll try and speed up a little bit. So application number 2. Continuous, nowhere, differentiable functions are everywhere. Are generic. So in this case, we're going to be looking at the set x is going to be the continuous functions on 0, 1 with the supremum. Is the supremum of all values, supremum of just the supremum, right? And metric, the standard metric that you get from that, induced by that norm. Then X is a complete metric space. With respect to this metric. And our statement is, as we said above, the set of nowhere differentiable functions in C01, C in this X is generic. Let D be the set of differentiable functions. So, let D be the set of functions differentiable at least one point. At least one point. Right, that's to say, it's the complement of the set that we're hoping to show is generic. Right? We want to show that D is meager. Okay, and as usual, this will hinge on a clever way of creating sets who exhaust D. So here's how we're going to do it. Let E sub n be the set of f in X such that there exists a point f star inside 0, 1 such that, so n is some natural number, such that f of x minus f of x star is controlled by n of x minus x star. Okay. So the picture is that here is 0, 1, right? And then there's going to be some x star in here, right? Here's f of x star. And you have that, if you look at lines of slope n and slope minus n, then your function is trapped. Inside those bars. Right? There exists some point x star such that this trapping happens. Right? Your set lives inside this butterfly. I'm sorry, your function, the graph of your function lives inside this butterfly. You can see that this is not always, if your n is fixed, your function might not live inside, might not be in E sub n, but any function, if you fix any function, then this is going to work for some n. Right? This is guaranteed to work for some n. Right. So then the union of these E sub n's is going to be that will exhaust. right? The x star will be the point of differentiability. Right? You take x star to be that point of differentiability, and so it suffices to show that each event is nowhere dense. So we'll do this in pieces. First claim is that each event is closed. Suppose you have a sequence that converges to F, right, in the soup norm. We claim that F must lie in each event. Right? In other words, each event is closed. That is, I mean that we want to show that there exists some x star in 0, 1, and some such that f of x minus f star is controlled by n minus f minus x star. So what we do is, each of the fn's has an xn star, right? And there's an infinite number of them in 0, 1, in the closed set 0, 1. And so you can choose a convergent subsequence, right, by Bolzano-Baire stress. So there exists a convergent subsequence of the xn stars. Call it xn k star. Converging to something that we'll call x star. Come over here. Now let's consider f of x minus f of x star. Right. Like I said, we're trying to show that that's controlled by n times the distance of x to x star. So we're going to sort of do the standard triangle inequality again. This is controlled by f of x minus f, so nkx. Plus f nk x minus f nk x star plus f nk x star minus f of x star. Now, we have that at each point we have convergence. Right? So certainly at x we have convergence, and at x star we have convergence. Right? So these terms we don't really have to worry about. We can make these, given any epsilon, there exists a k such that k exceeds k. These terms are smaller than epsilon over 2. The first and last terms So let's consider then fnk x minus fnk star. Remember, our goal is to show that that thing is smaller than n times x minus x star. Like this, fnk x minus fnk x star nk plus fnk x nk star minus fnk x star. Right, the point is that you can't just say that this is smaller than, we don't have control. This is f sub nk, right? This x star is not the key point for fnk, right? We want to incorporate fnk star into this so that we can throw out that information, right? So we say, okay, let's throw that fnk star, xnk star in, right? Now, we do have control over this part, right? This part, the first part is controlled by n times x minus x sub n star. And the second part is controlled by n of x nk star minus this. Okay. So now let k go to infinity. Now let k go to infinity, and what we get is that something is wrong, right? We can't let k go to infinity. Oh yes, we can. It's okay. So we let k go to infinity here, right? We let k go to infinity here, right? We get fk minus fx star is controlled by epsilon plus this thing as k goes to infinity. Let's say n x minus x star plus n x star minus x star, which is to say 0. Okay. And so we get this is smaller than n. So since this is true for all epsilon, we get the balance that we want for all. So we get that that thing actually is closed. So right. So Okay, so each of those guys is closed, and now we want to show that each of them has no interior. So last one. Plane, the interior. So let P be the piecewise linear functions. Continuous piecewise linear functions. And let these of M be the functions be those whose slopes all let's see, are greater than or equal to n in absolute value. So we want the guys who have bigger than m slopes. They'll be piecewise linear, and the slopes are all going to be bigger than some value in absolute value. And notice that when m is bigger than n, then our previous piece of n cannot have anybody in a piece of n, right? Because piece of n has to live inside that butterfly. If you're a piece of n function, you automatically exceed that butterfly. Okay, so now it's easy to see, it really is easy to see that the piece of n's are all dense in C0. You can approximate any continuous function in the soup norm with one of these zigzag guys. Right? It's sort of obvious. Right? If you have any function, you approximate it with a piecewise linear function. You approximate the piecewise linear function with one of these zigzag guys. The end. Okay. That's it. So then this implies that the interior of each piece of n is empty for you take n bigger than n, then every ball in C01 contains elements, so intersects P to n, which in points which are outside P sub n by the fact we said earlier. Right? Anybody in P sub n is outside of P sub n. Right? So the ball cannot be contained in P sub n. Right? So no ball can be contained in P sub n. So what we've just shown is that the set of discontinuities can be expressed. What we've just shown is that the set of functions which are differentiable at some point are contained in the union of these E sub n, which are closed and nowhere dense. Okay. So that means that the functions which are not differentiable everywhere are a generic set. Okay. We have 6 minutes. I don't know if we can do it, but I'm going to try to do the most important application. So this is the uniform boundedness principle. Here we go. This is also called the Banach-Steinhaus theorem. But it's more picturesque to call it the uniform boundedness principle. So if being a Banach space, you have L, a collection, a set of continuous linear functionals, and such that on some generic subset, E of B, we have the supremum of L of F for each L in L is finite. Okay. So for each so let's say a subset for each F in some generic subset of E, we have that the supremum of the absolute values over all continuous functionals in our chosen set are finite. Then the supremum of the operator norms is uniformly bounded. Uniformly bounded. The norm of everybody in that set of consideration is bounded by some constant. Okay. So, as usual, we define some sort of clever, exhausting sequence of sets. So let's consider the set E sub n being the functions in B such that the supremum of L of F is smaller than M over all elements of L. Well, as usual, we see that the union of these guys is going to give us all of E. Right? And we also see that further En can be written as the intersection of E and L, where E and L is the F and B such that L F is less than or equal to N, a closed set. And the point is that each of these E sub n is closed. Each is an intersection of closed sets. The E sub m are the functions where everybody in the set is smaller than m. See, that's the intersection you look at each L in L, and you say, well, what guys, on what guys are you smaller than M? You take the intersection of all those guys, and you get this E sub M. Right? So each of the E sub M's is closed. Okay. So E is generic. Is everyone okay? E is generic. Right? That means that wait a second, not generic. What am I saying? Sorry. Second category. What am I saying? So subset in the second category. E is the second category. E is the second category. So, sorry, I prepared this lecture at 3 a.m., I think. E is the second category, so that tells you that it can't be a union of nowhere dense sets. So, one of the, at least one of the E sub M contains some ball, contains some open ball. Right, let's say it's some open ball, some radius r naught, centered at some function f naught. At least one of the E sub M, let's call it E sub M naught. So that means that what does that mean? That whenever f minus f naught, the distance of that is less than r naught, so we just call it r, so I don't mix up the book. Whenever f minus f naught is less than r, we have that LF is less than equal to m for all L naught. Right? That's just the definition. Right? This ball lies in E sub M sub naught. In other words, if you lie in the ball, then you are in E sub M sub naught. Oh. But then, just by linearity, then for any G and B of size less than R, if we look at L of G, that's going to be equal to L of G plus F naught plus L of F naught plus L of F naught. By linearity. This is going to be L of G plus F naught minus F naught. By linearity, you say, okay, but now we have something, sorry. Okay, so I'm being a little bit, let me put the less than or equal here, and you can take this R to be smaller than that R. Okay, so let me call this R naught, and R is smaller than R naught. Just to make it okay. Okay. So then, this thing lies inside that ball, right? So we get that L of this is smaller than M naught, right? And L of F naught, certainly F naught lies inside the ball, and so that's smaller. L of that is smaller than M naught. Right? And so what we get is that for every L and L, if we look at L on the ball of radius r, then there's a uniform bound. Right? And that means that the operator norm of L is smaller than 2M naught over M. With this uniform bound for all L. So this is fun. I hope this is fun, super cool. Next time we'll see more nice applications of the Baire category. And that's probably how we'll finish up the course. We'll finish. I think we'll finish chapter 4, and that'll be a good place to start. In fact, we must start. Any questions?